Welcome, differential equation students. This is Dr. Sweeney, and this is our very first lecture for an introduction to differential equations. We're going to take a look at some key terms here inside of differential equations, and hopefully so that we can be on the same page in terms of the language that we're going to use. So let's start out with an example of a differential equation. Let's start out with s double prime of t equals negative 9.8 meters per second squared. And so what we know is that that's the acceleration of an object in free fall. Okay, moving towards the Earth. And what makes this a differential equation is the function relates the derivative, or second derivative in this case, of the function to the function itself. So for example, we see here that if we have s double prime of t, it's going to be related to s of t, which is our position function. Okay, and what we say is that s of t, okay, is the solution to the differential equation. Specifically, when we plug in s of t, what we're going to get is we are going to get s double prime of t, right? When we take the second derivative of s of t, we'll get s double prime of t, okay? And so that's the solution to the differential equation. We're going to have two different kinds of solutions. One's going to be called the general solution. The other one will be called the particular solution. And it just depends upon the particular circumstances as to whether or not we're going to be using this general or the particular. Okay? Now, we already know how to, in fact, find our position function if we're given the acceleration of the object. So what we'll do is we're going to take s double prime of t equals negative 9.8. And then we'll take that dt, and we're going to take the integral of both sides. Everything that we're going to do in our differential equations class is basically going to be ways in which we can get both sides to be integrable. That is that we can integrate both sides. At some point in time, we're going to need to be able to do that because that's how you solve differential equations. Okay? So every method that we're going to use is going to be intended to find a way to integrate both sides of the differential equation. Okay? So we do this and we end up with s of t, or s prime of t, excuse me, equals negative 9.8 t plus, and let's call it s prime of t. Or actually, we'll call it s prime naught of t. Well, better yet, let's just call it c1. We'll call it a constant, and that's going to be the first constant. Now, I called it c1 because I'm going to have to take the derivative twice, okay? Because I've only got the second derivative, then now I'm going to my first derivative. So now, to find the function itself, I'm going to take the integral again, okay? And what that gives me now is that gives me s of t equals negative 4.9 t squared plus c1t plus c2, okay? And so that, in fact, is my solution. What if I want to verify that this is, in fact, my solution? In fact, this is going to be one of those exercises or activities that you're going to have to do. What it means to verify is to show that s of t fulfills the differential equation. So in this case, right, what we'll do is we'll take s of t, and we're going to first take its first derivative. So s prime of t is equal to negative 9.8 t plus c1. Okay, so that's just the derivative of s double prime of t. And s double prime of t is thus going to equal, is going to equal negative 9.8. All right, and if we go back up, we take a look at our original function, that's it, right? S double prime of t was negative 9.8 meters per second squared. S double prime of t, again, is negative 9.8. Thus, we have verified that S is the solution to S double prime of t equals negative 9.8. Let's take a look at another common or like canonical differential equation as well. And we're going to use something called Newton's law of cooling. You probably have seen this one as well inside of your calculus class. But what you did with it was you didn't actually solve the differential equation. What they gave you was they gave you a solution, and they had you, basically take solve it implicitly, okay, take the derivative implicitly and show that, in fact, whatever function that you had was the solution to the differential equation. What we're going to do is we're going to actually go out and find that solution of the differential equation. So let's talk about Newton's law of cooling. All right. And so what Newton's law of cooling states is that if you place an object into some kind of cooling bath or a heating bath, depending upon which way you're going, that essentially the object will cool or heat to the temperature of to its internal temperature. Okay. So what that means for us is that means there's a general equation that we can use for Newton's law of cooling. We're going to start out with, we'll take the derivative, dt is going to equal negative k times t minus t naught. Okay? And so there's some things to notice about this particular differential equation. One, t is the dependent variable, right? It's the top variable, so t is going to be the dependent variable. Little t is the independent variable. K is the rate of cooling for the particular liquid, all right? And it is constant. It is constant in our case. And T naught is the initial temperature of the bath. So what we're going to ignore for right now, okay, is we're going to ignore the fact that maybe there's some, kinetic loss due to the fact that, the bath isn't infinitely sized. So we're going to say that the bath is infinitely sized and that, in fact, the temperature of the bath is going to remain the same. All right, so the rod is not big enough to actually change the temperature of the bath. It's so big, right? It's an infinitely sized tub, so consequently we don't have to worry about all those other issues. All right, what we're going to see here, though, is we're going to see that the rate of change for the bath, okay, is dependent on the temperature of the rod, which is T. And T is dependent upon time. But you'll notice in the differential equation, little t does not show up. So when we think about this, that's what's going on. Like we're saying, okay, so little t doesn't show up inside of this Newton's law of cooling thing. Only big T, only our temperature of the rod makes a difference in terms of the rate of change. Okay, and so that's another aspect of the differential equation that's really important. The dE, as we're going to call it often, is the rate of change. It's a derivative, okay? Or it might be the rate of change, right? Okay, but whatever it is, the differential equation is its rate of change, and in this case, it's going to only be dependent upon the temperature of the rod, upon the dependent variable. And so that's a little strange. It's a little different. It's going to force us to do some different things with this function, right, in order to solve using Newton's law of cooling. Okay, so in general, if we were using this, we would get the temperature of the temperature of the bath, okay, which is going to be, we'll call it big T or T naught, excuse me, right? The rate of cooling too, okay, or we may have to go out and solve for the rate of cooling, depending. We're going to talk about Newton's law of cooling more inside of the section when we talk about separation of variables, all right, or separable equations. And that's because this one is a very classic separation or separable equation. And so consequently, you'll see how that works. Okay, cool. And in fact, I'll produce an example of it. But what I wanted to show you in particular is that here, okay, T, right, is the dependent variable, and our differential equation is only dependent upon that. By the way, the solution to dt equals negative k times t minus t naught is going to be t of t equals something, which we are going to see in a later section. So let's take a look back at this question that we had about s double prime of t equal to negative 9.8. That's our differential equation for acceleration due to gravity, and s of t, which is negative 4.9 t squared plus c1t plus c2, okay, which was our solution, all right? So when I look at this differential equation, one of the things that I want to notice is that c1 and c2 are their unknown constants, okay? So we in fact have an infinite number of solutions for s of t, okay? And they're all going to depend upon something. They're all going to depend upon two things, okay? So s of t, right, is going to depend on, right, v naught, our initial velocity, and s naught, our initial position. Both v naught and s naught are called initial conditions. The reason why we have to have initial conditions is to notice that every time I take a derivative, I lose information about the constant. Okay, so when I take the first derivative, I lose c2. And when I take the second derivative, I end up losing c1. Okay, so I lose information about my function. All right, so consequently, every time I take the integral, I have to add that information back in by utilizing an initial condition. All right, and we've used that before as you've done differential equations in your calculus classes. Okay, these initial conditions, what they do is they transform like what this general solution, and we'll define that in just a moment, into what we call a particular solution, one that's dependent upon initial conditions. So S of t, okay, with its unknown constants is called a general solution. And any solution to a differential equation that has unknown constants for it that we have not included, okay, the initial conditions, is called a general solution. Okay, so that's a very important phrase because you're going to be asked either for the general solution or the particular solution. Okay, and so we have not included the initial conditions. On the other hand, when we add in the initial conditions, we get something called a particular solution. Okay, and the particular solution will not have unknown constants. Instead, it's going to have some very well-defined constants. So let's take it as an example. This function, y of x equals e to the 4x, and this equation, y double prime minus y prime minus 12 equals 0. Now, we'll notice there are no unknown constants. So what this is this is a particular solution. Okay? And what we're going to do, we're just going to go in and verify that, in fact, that y of x equals e to the 4x is a solution to y double prime minus y prime minus 12. We're going to say that y of x satisfies the differential equation. Okay, so what I'm going to need to do is I'm going to verify that y of x satisfies y double prime minus y prime minus 12 equals 0. So the first thing that I'm going to do is I'm going to take the first derivative, and that's going to be 4e to the 4x. Okay, then I'm going to take the second derivative, y double prime, and that's going to equal 16e to the 4x. So now what I'm going to get is I'm going to plug that back into my differential equation. All right. It was pretty simple to see it in the first case. Now this is a little bit trickier. We've got to actually plug it back in. So y double prime is 16e to the 4x minus, and then y prime is 4e to the 4x. Okay. And this actually should be a 12y. Okay. Minus 12, and then y is e to the 4x. And so what we end up with is getting 0. Okay, so y double prime minus y prime minus 12y is going to equal 0. That, in fact, is the solution to the differential equation. Nice, right? Okay, what if, though, we had a general solution? What if we had y of x equals, and what you're going to see for these ones is ce to the 4x. Okay, so now we have a constant. We have a constant in front of c. And so what we're going to need to do is we're going to have to show that this, in fact, also is a solution to y double prime minus y prime minus 12y equals 0. Okay, so what we do is we'll take the derivative. First derivative is going to be y prime equals 4ce to the 4x. Y double prime is going to equal 16ce to the 4x. And when we plug it back into the differential equation, we're going to get 16ce to the 4x minus 4ce to the 4x minus 12ce to the 4x, because that's our y. And that, you'll see, is also equal to 0. Right? So both the particular and the general solution are solutions to the differential equation. Okay? And the difference is that at some point in time, we were given an initial condition for y of x that will allow us to, in fact, solve for the particular solution. So now we have this whole idea of we have a particular solution and we have a general solution. And now we're going to talk about this thing called the initial value problem. An initial value problem is it's a differential equation coupled with a an initial or multiple initial conditions. Okay? And in order to help us understand this, we're going to get the idea of the order of a differential equation. Okay? So the order of the differential equation is the power or the degree of the highest derivative in the differential equation. And one of the things that we want to know is the number of initial conditions to find a particular solution, in an initial value problem is equal to the order of the differential equation. All right, so let's say, for example, we had that previous one. We had y double prime minus y prime minus 12 equals 0. Okay, we'll notice that this is a second order DE. Right, we're going to say it's second order because it's got the highest degree of the derivative it's a double prime, so it's a second order DE. And so it requires two initial conditions to get the full particular solution. Get the full particular solution. In fact, not only that, what we'll notice is that the number of solutions to y double prime minus y prime minus 12 is going to equal 2. So there are actually two general solutions, okay? And each one of those general solutions is going to require an initial condition in order to, in fact, get the particular solution to the DE, okay? Let's take a look at another example. Let's say, for example, that I have y double prime or x squared y double prime minus 3xy prime plus 13y equals 0. When I look here, I'm going to notice again, this is second order. It's going to have two solutions. Both will be represented in the general solution, and it will require two initial conditions to find a particular solution. Let's take a look at one more. Let's say, for example, that I've got sine x y triple prime minus cosine squared x y double prime plus 2y prime equals 0. Okay. Again, now what we're going to notice is this one is third order. Okay. It's going to have three solutions. Okay. And it will require three initial conditions. Excuse me. It will require three initial conditions. So we've defined the order of the differential equation as the highest derivative or highest degree of the derivative. Okay. And that will define for us the number of solutions to the differential equation and the number of initial conditions as well that will be required to find a particular solution. The final term, or the final thing that we're going to look at for this particular section, is this whole idea of identifying the particular kind of the differential equation. So as we go through and we look at differential equations, the solution method that we're going to use in order to solve the differential equation or to figure out what equation would satisfy the DE is going to be really dependent upon identification of the differential equation. Okay, so what we're going to look at now, all right, is this thing called the linear differential equation. So a differential equation that can be written in the form of a naught x y to the n plus a1 x y to the n minus 1 plus an x y equals f of x, okay, where a naught, okay, a1 all the way down to an are functions of x only, is called a linear differential equation. So you may have noticed as we were going through and doing the differential equations that these differential equations will have y's in them, okay? But what you may or may not notice is that the functions that are in front of them, okay, and there will be functions in front of them, may or may not actually have any y's in them at all. If they don't have any y's, if they don't have any of the dependent variable in them, then what we say is that they are in fact linear, right? And in fact, constants represent functions of x as well. Right? So for example, okay, we have something like 3x squared y double prime minus 3x y prime plus y equals 6 sine x. Now what this is called is this is a linear differential equation because we'll look at 3x squared, 3x, and 6 sine x, and 1, there's a 1, it's actually implicit there, are all functions of x only. So this is in fact linear. It's a linear differential equation. On the other hand, if we took something like this and we said sine y, y triple prime, minus 3x y prime plus 2y equals 7x squared. This is nonlinear because this first function here, the sine y, is in fact a function of y and not a function of x. Okay? And there's no way for us to get rid of it. There's no way to get rid of that sine y function, and so consequently we end up having it be nonlinear. Another one that's a bit more common would be something like this. Let's say, for example, we have y triple prime minus 3x y prime plus, or y double prime plus 3x squared, y prime plus 2y equals 8x squared y squared. Now what we want to see is that f of x, and we should add in that, in fact, f of x also has to be a function of x. Okay, we'll see that f of x is not a function of x only. So that means that this function is nonlinear. All right? Just to emphasize that in order to have something be linear, we have to have all of the functions in front of each one of the derivatives and the function that we set our differential equation equal to be functions of x only. Right? So if we go back up here to make sure that you get that change, it can be written in the form a naught x y to the n plus a1 x y to the n minus 1, right? All equal to f of x, where all of these, the a naught, a1, an, and f of x, are functions of x only. And that's what makes that function linear. Okay? We're going to be utilizing these terms quite a lot, all of them: linear, initial conditions, initial value problem, general solutions, particular solutions, satisfaction of the equation, verifying that in fact that the solution is a solution to the differential equation. All of these things are going to be used quite extensively throughout this chapter and beyond as we work with more and more with differential equations. So what I want you to make sure that you do is I want you to make sure that you understand what I'm talking about when we talk about them. And if we have any issues with these as you come up in class, make sure that you do ask, like, hey, what's the general solution again? Or what's the particular solution, right? So that we can make sure that we're very clear on what it is that I'm talking about, all right? The better that you understand these kind of things, the better you can talk math, and the better that you can do the math.